Hey there, this is another edition of Kung Fu Physics where we're currently working our way through practice physics GRE problems, one at a time. The one I want to look at today is a mechanics problem. It's number 61 off of the 1992 exam. Looks like that. I've done this in conjunction with some of the other problems that are about the same type of mechanics thing, being physical pendulums, small oscillations, and whatnot. So there are some other problems posted. If you're interested, look those up. A lot of times in the taglines, or in the search words, I guess, whatever you call them, I will put something like that. And I may have to go back and edit those too to get them a little bit more useful and searchable. But anyways, it's a physical pendulum problem, so let's just do it. As usual, I like to look at those answers. Sorry on the green, it's a little hard to read that. You've got a couple fractions there. You've got fractions under a square root. It doesn't help me, obviously. I'm going to go ahead and start the problem. I can take a very quick glance at the diagram and then start. It's number 61. A long, straight, and massless rod pivots about its end in a vertical plane. In configuration 1 shown above, two small identical masses are attached on the first end. In configuration 2, one mass is moved to the center of the rod. What is the ratio of the frequency of small oscillations and of configuration 2 to that of configuration 1? Okay, sorry, kind of hard for me to read that. Doubly hard because I'm looking off of the webcam and the printout is off the side of the page there. As usual, though, I hope you have this problem sitting in front of you while you're watching this. It will probably be hard otherwise, but let's go ahead and get started. I will admit freely that I totally botched this problem in that I wasn't able to solve it fast or anything like that. I just, totally took my time with it, and I kind of got there. I kind of made some dumb mistakes along the way. But needless to say, I wasn't happy with doing it in under a 2-minute time frame, that's for sure. It's a hard problem, I would say, but it can be done in 2 minutes, let's put it that way. There are certainly several ways to do a problem like this. I would love to see if anybody else out there is recording videos and wants to post a comment video or a reply video or whatever with a better solution. I'm always welcome to those, and in this case there's probably some glaring ones out there. But anyways, so first things first, when they ask you for a ratio, it may be a little pedantic to do it this way, but for me, I write it. I actually write what they want to start. So the frequency, I'm going to write omega of configuration 2 to the frequency of 1. And so, of course, what that means, what that implies, is if I can find the frequency of the second configuration and divide it by the frequency of the first configuration, that's when I would get one of those fractions popping out. So these are what I'm looking for. Now, here is where I tripped up a little bit because I committed one equation to memory, and for some reason I just grabbed it and started using it. And I was using the periods instead of the frequency, Oops. But you can manipulate them easily if you remember one, of course. And so I'm going to put these up there. I would go with one of these as memorizing because I've done several problems with physical pendulums. It's kind of in that realm of being a advanced-y type topic that's uncommon in freshman physics, that they want you to know. They don't want you to know it for graduate school. They just want you to know that you were a good student and studied all sorts of stuff out of the realm of the normal when you're in physics. So these physical pendulums and small oscillations you see in a lot of problems on the physics GRE. I would memorize one of these. Omega equals square root of mgd over I, or the period t equals 2 pi times the square root of I over mgd. And you remember all your equations, hopefully, that relate angular frequency to a period, to a regular frequency, or whatever. And you can manipulate all those. If you know one of these, you can easily get the other one, of course. Of course. We're going to use that one there for omega, though. So I'm going to set this up as one big ugly thing here, and just it works. I mean, it does work to do it this way. So omega 2 over omega 1. Now, one of the things you'll realize early on is that a lot of this crap cancels out, and you can save yourself a lot of time doing that. Okay, so you know what, and I'm wasting time as I say that, which is funny. So I am going to start plugging. I'm going to start plugging in for omega 2 and omega 1 here. So what is the mass? Well, we're dealing with 2m times g. What is the distance to the center of mass in the second configuration? Okay, that's what is being asked for in this formula, the distance to the center of mass. Way important to recognize that. I think if you look at that problem, you're going to realize that it's 3/4 of the total distance. I'm just going to call that d. The d will cancel out. What's the moment of inertia of the second mass? Now, this is the only tricky part of the problem. You need to use, I personally would say using parallel axis theorem is a slick way to do that problem. I'm sure there are other ways, but so in parallel axis theorem, you basically condense the whole thing and treat it as a point particle rotating around that, and so that would be 2m, because I've got two masses in as a point particle, acting at a distance of 3/4 d squared. So I'm treating it like a point mass, and that adds to the moment of inertia as 2m, or excuse me, as mr squared. And in this case, I've got two of them. I'm using a 2, whatever. And then it's at a distance of 3/4 d squared. Then I have to add in the moment of inertia of that object about its center of mass. So what is the moment of inertia of two particles going about a center of mass? Well, there's two of them, and each one of them is going to be m times the radius it's acting squared. And again, or excuse me, not again, those are each acting at a distance of 1/4 d squared. Blah, blah, blah. This guy talks so much, I know, but for the sake of these videos, I do a lot of crap that you wouldn't usually be doing if you were actually blazing through this test, hopefully. You'd be making lots of these little mental shortcuts. Right? Okay, so omega 1 is quite a bit easier. You just got, it's two masses acting at a distance g. The distance is just d. Hopefully you can see that. And then we divide by I. You know what? I need to write this up here just to have it on my board to be a little more thorough than I'm being. This is the equation that I'm just doing for both of these situations, okay? And then down here, what is I for the moment the two masses squished together? We're going to treat them as a point mass of mass 2m, and so we just have 2m acting at a distance of d squared. So much is going to cancel here. You notice the 2m is out, is out. The G is out, is out, is out. The D over D squared is out, is out, is out, is out. Okay, so you just get under the square root sign. You're going to get 3/4. This is just 1. I mean, everything canceled out of the bottom. Everything. So you get 3/4 divided by 3/4 squared plus 1/4 squared. So 9/6, well, you know what? Yeah, whatever. 9/16 plus 1/16. So multiply everything by 4. You get 4s down the bottom. Basically, you get 3 divided by 10/4 under the square root, which is equal to 12 over 10, equal to 6 over 5, so all still under the square root. Square root of 6 over 5. Ugh. Pain in the butt to get there, right? But that is one way of doing it. I welcome a faster way of doing it. I think that problem could be done fast if you were real familiar with these physical pendulum problems. Otherwise, this problem is certainly in the moderate level as far as difficulty goes. Otherwise, this problem is certainly a time trap potentially, right? We gotta check our answer. What am I doing here? It's 6/5. Square root of 6/5. Is that in there? Yeah, there's an answer that's like that. Answer A is 6/5 to the 1/2, and that's what I would be picking. So, very long-winded description, a little bit about that. This is type of a problem that would be leading you down the road to studying more, if you haven't already, about parallel axis theorem and physical pendulums, equations regarding physical pendulums, because you can rest assured there will probably be at least one of those problems on your test when you go to take the physics GRE. So that's all for now, and thanks for watching.